All right, we'll get started here. So we're the last sort of topical discussion of the meeting. So and we're talking about so first it's Philip and me. I'm Shane Davis. We're both at UvA, and so there's been a lot of discussion of post-processing and mock observations already. So we thought we would just continue some of the conversations, and so. I thought I would start where we thought we'd start with just a little bit of a pedagogical first slide, just to highlight some of the issues that come up with post-processing. And I know a lot of you already know this, but I think there's probably some people in the audience who might benefit from a refresher. So typically when we solve these equations, we're solving, so typically when you're doing mock observations and post-processing, you're solving some version of the radiation transfer equation, and then possibly coupling it to a recomputation or a computation of thermodynamic properties like the temperature, atomic levels, molecules, and dust. And so just to review, right, the radiation transfer equation is an equation involving the specific intensity. It's a function of angle and frequency. This part on the left is just the transfer. This n hat here is a direction vector. It's a unit vector. So this transfer is done along rays, so you pick out particular directions to evolve the intensity. The intensity is pretty close to what observers want or what observers measure in their detectors. And then on the right-hand side, for the sources and sinks, we have an emissivity, which is a function of frequency generally. It's also generally a function of temperature and density in the simplest case, but it can also be a function of dust properties. Can be a function of atomic levels and ionization states and all these complicated variables. The same is true for the opacity. So we have both absorption and scattering. These take energy essentially out of the beam. So that's why there's a minus sign here. So this is a source of photons. This is a sink of photons. Again, these can be very simple, but they can also be very complicated functions of the levels and ions and stuff. And then last, we have this ugly term here, which just represents the scattered light. So this is just some redistribution function. And all I'm doing here is writing intensity as a function of frequency and angle. And so basically what happens here is light is scattered out of the beam here, and then it's scattered into the beam from all the other angles. Okay, so scattering couples all the angles together. So, so basically, this is a fairly easy equation to solve if this is just a function of simple properties like the gas density and temperature, which is what you have when you have local thermodynamic equilibrium and simple opacities. And you don't have this scattering term, because then you can just calculate this, solve this equation along individual rays. And that's just solving basically an ordinary differential equation. What becomes hard for a lot of post-processing is that when this is a function of level populations, and those level populations depend on the intensity in the radiation field, or when you have scattering and you've coupled angles together and you turn this into an integral differential equation, and then you have to deal with those things. Okay, so that just kind of gives you some background of what's going on. Now, this is not the simplest case because this is not written in a covariant fashion. Of course, when you do general relativity, you have to solve a covariant version of this, and then you have to solve it along geodesics. And of course, I left out polarization, and polarization can be very important. It's probably less important for the black hole binary case, because we only have one polar emitter. I don't think IXP is going to be able to look at black hole binaries very well. But of course, it's very important for the protoplanetary case, because often what you're seeing is polarized light. In order to look at the sort of dust scattering from the disk around the star. And then I just wanted to highlight a couple of the methods that people use, and this is why I wanted to do this introduction, or we want to do this introduction, is the simplest method is ray tracing. Ray tracing is great when you don't have to deal with scattering and you don't have to deal with recomputation of your thermodynamic variables. You just put your simulation on a grid, you integrate backwards, you get images, you get spectra, and you can do that relatively quickly. Okay, so for example, we already were hearing about the EHT collaboration. They did there's a bunch of ray tracing codes, that's why I didn't name any. they did about 34 GRMHD simulations and 60,000 ray tracing calculations. So as a function of time and different angles and other assumptions. So that's great if you don't have to do any recomputation. If you do, you have Monte Carlo methods are usually the method of choice. Monte Carlo, you move photon packets through your simulation domain. And Monte Carlo is often used when you're recomputing the temperature or when you have scattering and you have to deal with this redistribution. Monte Carlo is used a lot in the protoplanetary disk case, so codes like RAD-MC3D, Hyperion. It's also used in the black hole case. Julian showed us some examples using the Pandorata code. There's other codes like GR-Monte, RADPOL. There's a bunch being developed. Generally speaking, for black holes, we're talking about Compton scattering, electron scattering, and for protoplanetary disks, we're talking about dust scattering. There's other methods, short characteristics, and then the last thing I just want to mention, oftentimes there is use of things like photoionization codes like Cloudy and XStar, which observers use, but those are sort of 1D codes and sometimes not easy to couple to these simulations. Okay, so that was an introduction. Unless anyone has any questions on it, we thought we'd go to some motivating topics.
Yeah, so that's really just a recap from what we have heard during the week. And a lot of those questions have already been discussed in other discussion sessions, other talks. So it's really just kind of where can we find a new angle on any of these topics. But I think these are really just kind of talking points we threw out there or are throwing out there now. So like, yeah, what do observers want? Which simulations are actually worth post-processing? I think a lot of these questions came up during the week. How do we do time dependence of simulations, single epoch, time averaging? And then how do we ultimately bridge the gap between simulations and models? Like, can we build something on top of simulation suites that then can be actually used to fit to data? So these were kind of questions that we identified that we wanted to bring up. And I think then also a few people sent us slides. So I think, who do we have first up?
Well, we have Xiaowen first, but can I just add, so for example, for which simulations are worth processing, we already heard Matthew Bates say that 2D simulations aren't worth post-processing, right? So is that true? You know, did people want to argue about that? And I think the other thing I'm really interested in is the last question of how do we bridge the gap between simulations and models that can be fit to the data? Because we have a lot of beautiful post-processing, we have a lot of beautiful data, but I think the hard part is comparing them together when you can't actually, you know, get a goodness of fit and various things. So, and I think that will come up in some of these slides.
Maybe we can settle this question, like whether 2D simulations are worth post-processing first, since I feel like maybe we can get this out of the way.
Well, maybe Ryan Westernacker, Schneider, or Zoltan have or Dutpol.
I was actually, I was asked Scott a very similar question about this earlier, and because, you know, they do these great post-processing of their results, you know, which have all this detail and it's 3D, and it may be the case that, you know, you might imagine in your head, okay, you know, there's a 3D structure that we're assuming is going on, but we're collapsing it to 2D. And then if you reintroduce that 3D structure, you can ask, you know, do you get something similar to what people get in a full 3D calculation? If not, you can ask, is there a way to recalibrate our models using these 3D calculations to post-process in a smarter way in 2D? And I don't really have a complete answer to that question, but my guess is you could gain a lot of advantage out of that, because you can, in 2D, you can go to longer time scales and do higher resolution.
Yeah, just on the 2D thing. I mean, obviously, if your system happens to be face on, then that's fine, right? if your system isn't face on, then, I mean, yes, you can try and reconstruct the three-dimensional nature of the disk. So for example, if you know the temperature at each radius, you could fit a Gaussian density profile, right, with Z and try and reconstruct the vertical. And then you could look at an angle. So yeah, you could do some of that with 2 dimensions. But just, it also depends a lot on what wavelengths you're interested in. So like, for example, I mean, obviously I work on protostars, not black holes, but for dust, for example, at ALMA wavelengths, that's generally large grains have settled to the midplane, and therefore the distribution of dust is very 2-dimensional, actually. And so, you know, sort of converting 2-dimensional simulations into ALMA dust maps would be quite good. But if you then wanted to go to, say, scattered light infrared observations, then the scattered light all comes from the surface of the disk, and that's when you'd have to then try and reconstruct the 3-dimensional nature of the disk and view it from an appropriate inclination and so on. So you can do it with 2D, but it does involve quite a bit of work.
Okay, so 2D is allowed, but under strict conditions. Yeah.
Judith here in the back. I also would like to advocate for the 3D, and the reason is that we found that the extinction is the main problem for most of the wavelengths, like what we are interested in protoplanetary disk, near infrared, mid infrared, even far infrared. And even in the ALMA wavelengths, we have found that 2D versus 3D does give a different result. So because of the vertical extinction, you should do 3D. And also it's not true that the dust is completely settled into the midplane. One reason is the dust diffusion. The second reason I just showed that the planet can also stir up the disk, dust disk, and therefore you don't see down necessarily down to the midplane.
Did anyone want to comment on any other simulations we shouldn't post-process before moving on?
Yeah, I guess I'll just add to what Judith was saying, is that it also matters what you're doing with the dust while you're running your simulation, and that painting it on afterwards can give you the wrong answer, again, depending on what you're wanting to do. I sort of, maybe to follow on what Matthew said, if you wanted to do scattered light observations, if you did 3D and painted the dust, you'd probably be better than doing 2D with no dust. But if you want to do something with ALMA, then you're probably better off, you know, really thinking about the dust.
I also believe that radiative transport inside the hydro going to give you different results, because you have consistently calculate the temperature there. And given that your observation not only depends on the density, but also very much on the temperature, I personally have hard time believing the isothermal work, which then assumes some kind of temperature, because then what do you exactly do for the mock observation? So I would say radiative also.
So getting the thermodynamics right.
As an outsider, I just have like a sort of maybe helpful question or pointer here, you know, for the protoplanetary observations, right? This sort of ties into the later question. I mean, 2D simulate, right? You run 2D simulations because they're cheap and you can run lots of them. And so you can explore a very wide parameter space. And so the question, I think, is really, how are you comparing your observations to the simulations, in the sense of like, are the 2D simulations worth post-processing? I think you have to ask yourself the question of what specific question are you trying to answer by comparing those 2D simulations to the observations. And, you know, there might be some circumstances where doing some of these halfway house reconstructions are worthwhile doing. And there's probably not like a single answer. It's just a question of, it really comes down to that last question of like, how are you bridging the simulation observation? Yeah. Just my 5 cents.
Joan. Oh.
Oh yeah, Mark and Vera here. So this has gotten me thinking a lot. You know, a few years ago I would have said, let's use 2D simulations because we can run them for so long to really explore parameter space and see what are maybe the most likely systems, and a lot of that work, as we see, has been done. Personally, I think we should think heavily about how to now utilize that as starting cases, maybe run in 2D to saturation state of some way, and then see how long we have to run a 3D simulation, starting from that as initial conditions, popping them up into 3 dimensions with B field. Because with full radiative transfer and GRMHD, I'm not sure we'll, in the next 10 years, get to the thousands of orbits we might need, but maybe we can have step simulations that give us radiative snapshots of systems that are, covering parameter space from what 2D tells us.
Yeah, regarding the 2D, so when the ARMA atrial tau image was published a decade ago, at that time, there were almost no code which can do 3D together with dust particles. So at that time, dust particle is way more important than the third dimension because particle will trap into the gaps which explain those gaps. So all the all of the synthetic images for atrial tau, they are all done in 2D simulations and then part of the disk post-processing. So it depends on the codes. At that time, because there's no 3D with particle, every physics included, people do 2D.
Just me again. Just on this running calculations for a long time, at least in the stellar context, again, I think it's probably overrated for 2 reasons. One is if you take a 50 AU binary, orbital period maybe 1,000 years, depends on the mass, then obviously it won't have done more than about 1,000 orbits since it formed, because it's probably only about 1 million years old. So I think these things that, if you have to run for 10,000 orbits or something, then at least in the stellar case, at least observational separations and so on, the things they're just not going to be that old. And then the other thing is these very pure simulations where you have a constant m dot and so on. I mean, you've seen from my star formation animations that things don't have constant m dots for 1 million years, right? They vary on timescales of probably hundreds to thousands of years. So again, this idea that everything is exactly the same for 10 million years just doesn't happen in star formation. So keep that in mind as well.
I think I was just about to ask, actually, maybe to some of the black hole people to comment on this. Is certainly in the star formation and probably the planet formation context, if you're interested in observational comparisons, you may never be in steady state. I don't know how you deal with that in any reasonable fashion. But for the black hole community, I'm wondering, is there a regime in which you really think that this steady state is the right answer, or is it the same problem and you just don't know the initial conditions?
I could say something. I think specific, Caitlin, to your question, I think generally everybody assumes AGN disks are constant m dot. But in fact, I think you're probably right, because if you ask the question, what is the viscous inflow of time from the point in the disk where the tumor Q parameter is 1, it's actually comparable to the lifetime of quasars. So I think it's possible that an equilibrium is never really established, even in general. But then the other point, the more general point, should you do a huge number of orbit 2D simulations or not? Maybe stellar case is different than the black hole case, at least for the decoupling issue, because the black holes run away and start to be driven together by gravitational waves. And that process, starting from a radius separation where they're well outside this regime and going through this decoupling epoch and then merging, you do have to run many more than 1,000 orbits.
And I was just going to add that observationally, right, we see things like changing state quasars and other things that are clearly not steady state. So yeah, it's definitely a concern for us as well.
if there are no more questions, we do have some slides. I think that if people want to comment, we can keep. Good. All right.
Maybe we can synthesize like a handbook for how to not compare simulations to observations from this discussion, and people can send it, like maybe we can create a Google Doc or whatever. People can like put in what they think should not be done, and maybe that will enlighten us to then have a flowchart of what. Oh, maybe this will then allow us to have like a flowchart or more of a path of like what could actually be compared.
Mm-hmm. So we did have some slides provided, and so we should probably go through some of them. So actually we only got slides from black hole people, so I twisted Xiaowan's arm to provide some things for planets. So he's actually, maybe he can talk a little bit about the things, even though it's not necessarily his own work.
Yeah, I was asked by Shane to provide some slides, and I decided to get some from the people here. So some of the slides are from the people, the paper with the first order here, so maybe you could discuss more. But here I just want to show what has been done in protoplanetary disks and see if these will be useful for different community. So I have two slides. One slide is about imaging, kinds of post-processing. We could get images out of them. Another one is SED and the lines. So in the imaging, we can do sub-millimeter continuum, as Judy showed, and sub-millimeter line observation, AMA kinematics, and then near-infrared observation. These on the left, these are all intensity, full intensity. On the right is that we can do polarization, and we should do is because AMA can do dust polarization, linear polarization now, and there is no code right now which can do kind of circular polarization for lines. So there is a blank there, but potentially that's an important aspect in future with when AMA could get line circular polarization, you could measure magnetic fields. But there is no such tool there. And then
can I ask, is this all Monte Carlo?
For all of these?
Or is it ray tracing?
Yeah, these are all, I don't know how Judith did the intensity. Monte Carlo, yeah. Josh, you did Monte Carlo? Yeah. But yeah, they are all Monte Carlo. Yeah, so these are all Monte Carlo. The polarization for near-infrared is important because then you could get rid of the central star and highlight this feature. But the caveat is that the features you see in the polarization may not necessarily reflect the full intensity. So if you compare left and right for the bottom panel, you see that, oh, you see features in the polarization and they're very bright on the right side, but if you look at full intensity, that may not be the case. So that's about the imaging. I don't know if Josh or Judith have more comments. No? Yeah, so this is what we do for protoplanetary disks, mainly compared with AMA and ground-based 10-meter telescope for imaging. Yeah.
Should I go to spectra?
Yeah, the next one is the spectrum. Spectrum, we do SED and we could get the lines. On the right side is H-alpha lines for magnetospherical accretion. And in protoplanetary disk study, we are still, for this post-processing are still not very advanced. These are from 1D plane atmosphere model, and you kind of stack them together along the disks. So basically, it's not processing three-dimensional simulations. So these are, it's more like you build a model, analytically build a model, and do radiative transfer, assuming plane parallel or giving some geometry. But these are not from the post-processing simulations. So this is a part where probably we should do more post-processing simulations to get the lines and SED, but that is probably very difficult, especially for lines. Yeah.
So we have some more stuff on thanks, Xiaowan. We have some more stuff on black holes. Did anyone want to comment on post-processing and what's needed in protoplanetary disks before we move on? Is there a big missing aspect to it? No takers.
Agreement on this. That's great.
Do you want to go to the? Is it Ryan's next?
Yeah, I think then we had Ryan, who should be on Zoom.
Yep, I'm here.
Go ahead. Your slide is up.
Okay, so my name is Ryan Westernacher-Schneider. Here I'm showing some work that we posted last November and some work we're currently doing. So in the top half of the slide, so we were doing 2D simulations of a black hole binary, equal mass. So in the top half of the slide, we're looking at light curves from circular binaries. And what I want to focus on here is just the frequency content in the light curves. So circular binaries show two periods, sort of the well-known lump, which is a slower period, and there's also a faster period, which is almost the orbital period, which you can see here. So here I'm saying optical and infrared. You don't need to take that too literally, because you could scale the binary parameters to sort of change what bands exactly these are. What you should think about is that the lower energy bands are sort of coming from larger radius. And so what you can see here is that in lower energy bands, you still have a strong lump period. That's the red curve up top. But the orbital or the nearly orbital modulation gets significantly smaller. So that's telling you sort of spatially where is the modulated emission coming from. The lump modulated emission is coming from larger radii. If you go deeper in, then you've got larger amplitude of this fast oscillation. One question, so this is a circular binary, circular equal mass binary. One question is, what is this fast period here? So we've been investigating that, and the answer is that the fast period is the frequency of mini-disk interaction. So here's a snapshot where the mini-disks are about to interact. So what we've found is that the mini-disks sort of generically develop an eccentric morphology, and they precess in the retrograde direction. Their phases, the relative phases, sort of approach 180 degrees, and so then they precess into each other at a frequency that is giving you this fast modulation here. It's not always obvious that the mini disks have an eccentric morphology. We think this is why it was not seen generally before, because it wasn't that obvious. You know, the mini disk is like a dynamical thing, and so you can't necessarily see a subtle amount of eccentricity in it. But if you play with the parameters, you can make the eccentricity a lot more obvious, which is what allowed us to arrive at this interpretation. The fact that they precess in the retrograde direction, we currently think this has to do with the fact that the disk has a finite scale height. So just, if I can paint a rough picture, you know, in these simulations, we use a softened gravitational potential. And the softening is supposed to represent the fact that the disk has a finite scale height. So, you know, you take the hydro equations and you vertically integrate them. A column of gas will experience a little bit weaker of a gravitational force compared with Newtonian, simply because of its non-zero height. So imagine if you're a test particle and you're just orbiting a single black hole that has a softened potential, and you come in on a eccentric orbit. At large distance, the force is approximately Newtonian. So you're on a Euclidean orbit, and once you get close to the black hole, the gravitational force is weaker than Newtonian, and so the particle will not wrap around the black hole as much as it would as if you were using a pure Newtonian gravity. And so the particle will basically reach large radius again, but the apoapse will have precessed in the retrograde direction. So I don't know if you could figure that picture out just from words, but that's what we currently think is going on. And so we would expect that essentially you would see this if you ran for long enough in 3D simulations, provided that the scale height of the disk was sufficiently small. So you had to go, above Mach 10, and not really sure how long you'd have to run for to see this effect. You sort of want to be in the regime of validity of the thin disk, but not razor thin. I'll pause there before moving on to eccentric binaries in case anyone has a question.
Yeah, this is Mark Vera. It's very interesting. I just wanted to comment. So as one of the tests for the simulations I showed, I ran inviscid hydro simulations restarting from the evolved circumbinary disk. And the mini disks that form, they're inviscid, so they don't run very, they don't really accrete in a normal way, but they look akin to this. So I think a comparison might be worthwhile.
Oh, that's very cool.
And those would have the post-Newtonian effects. So.
Right.
Good. Okay.
Can you also tell us what exactly you mean by interaction between the mini disks? Which fluid element is striking which other fluid element and leading to dissipation?
So their extent is such that they just reach into each other, and so they just crash into each other and sort of trade mass.
So is this basically the streams through the L1 region that we've all been talking about?
I'm not sure which stream you're talking about, but imagine these two disks, right? They're so eccentric that they sort of reach across the midpoint towards each other.
Oh.
And when they precess into each other, then they're overlapping, and so you get a mass trade.
Probably a longer conversation.
Yeah, maybe in the interest of time, Ryan, if you could go on to the eccentricity part so that we can then have Scott afterwards for another 5-10 minutes.
Sure. So at the bottom part of the slide, we're talking about eccentric binaries. We fixed the eccentricity to 0.45, which is sort of motivated from recent work that we believe that might be an equilibrium eccentricity under gas-driven evolution. So the light curves are very different. Here I'm showing 10 orbits long instead of 60. And we see that you can get a flare happening between once and 3 times, maybe more, per orbit. So imagine what the implications of this would be if if pulsar timing starts telling us about the population of these binaries and telling us sort of what their periods are, and then large electromagnetic surveys see a light curve like this, and they just assume that the period that they see is the orbital period. They would assume that the binary is more compact than it really is, and therefore it would be emitting a larger gravitational wave signal, which might be in conflict with pulsar timing data. So it's important to recognize that this is a possibility here, that you could get 3, maybe even more flares per orbit. And the hydrodynamic origin in the bottom right. So there's a mini-disk interaction that occurs at periapse. That's shown in red here. There's also accretion stream crashing into an accretion stream. That's sort of depicted in the snapshot in green. And then there's accretion streams crashing into the cavity wall, shown in the depiction in blue. So these are just three sort of distinct events that correspond to these optical flares that we see in the plot. And you can imagine if you went to even higher Mach, how many distinct shock heating events are occurring. So that's why I say, 1 to 3 plus times per orbit.
Okay, are there further comments, questions?
I have a question on the first part, actually. So I thought the conv is 5 orbital period. Here is 10 orbital period, or maybe I'm missing something.
Yeah, so in our simulations, in order to generate light curves, we went beyond the isothermal equation of state. And it's been seen already back in 2015 that when you use like a gamma law equation of state, the lump period is longer than 5 orbits. It's about 10. But it also depends on Mach number and stuff. We did a large suite of simulations in this paper here. And the range of lump periods was between something like 5 to 10 orbits. There's also a lot more going on than is usually discussed about the lump. There's like multiple flow patterns that can propagate along the cavity wall, and what the lump actually refers to is ambiguous, but I don't have time to get into that.
Okay. Yeah, thanks very much.
Thank you.
That was very nice, and it's also perfect handover to Scott.
So you gave us 4 slides, Scott. Did you want to talk about all of them, or is there 1 or 2 that are?
I just wanted to, I don't know.
Wait, do what you want.
Yeah, you can handle it.
I've talked about this last week, though. I know not everyone was here. But I mean, we ray trace our simulations. We use so we ray trace our simulations. We use, but we kind of make it consistent with our thermodynamics by integrating the radiative losses to create a thermal spectrum that we emit from a photosphere, and we transport through an optically thin corona that we model as a single temperature corona. It's supposed to approximate, AGN spectra. So it allows us to get a full SED of these things and understand the variability as a function of wavelength to see maybe where we should look for the variability and associate with the different components of the accretion flow. You can advance if you want. I think that's. In the optically thin limit, you can explore mass inclination effects. When it's really inclined, you're going to be peering through a lot of the accretion flows. So in the optically thick limit, you're not going to be seeing anything except the edge of the simulation domain. So you have to kind of set, if you want to look at inclined things, you have to set the accretion rate to be low so that you're optically thin. And then, because this is in GR, you can get these lensing flares that enhance the intensity of the accretion flow of one black hole that's in back of the foreground one as it passes by. And so you get these lensing flares that kind of remind us of the spiky source that Dan and others have been looking at.
So is that what PhD
Well, this is the X-ray emission. So yeah, and the upper left hand is synchrotron, which is kind of maybe what EHT would see. And that's a spin-in case. So you do see these jets. So you see these synchrotron jets come out from them too. And I don't think we've done. Yeah, so I guess the movies aren't synchronized, but yeah, I don't know what the variability of the synchrotron is, but when it's lensed, yeah. So I think we're still working on that. Okay.
Should I advance?
And I want to point out some people are doing Monte Carlo in numerical relativity calculations of plasmas. So this is using the Ponderata code Jeremy Schnittman used, and other people like Goddard, not including myself, have been doing these accreting, uniform plasma simulations, and then Jeremy with his Ponderata Monte Carlo code calculated like the synchrotron emission using the plasma properties, and an image of that is in the upper right hand corner. So this is just kind of give you an idea of what people are doing in the field.
Do you want to do your comment and questions?
Oh, thanks. Yeah, I'm sorry, I forgot. Yeah, I think it's really, we do all these simulations, but we need to keep our eye on predicting observables. So it's important to have this kind of pipeline in place so that you can then kind of almost, immediately, not immediately, but quickly, make a, electromagnetic prediction. And then, what missing physics or things do we need? How do we're particularly interested in, because AGN are so wild, how do we distinguish binaries from single AGN sources? And do we need more physics, or do we need to do this in a numerical relativity sense, or can we kind of paint on the orbital, effects, the kinematic effects?
Well, if I can answer, I mean, I think one thing that's been bothering me the whole meeting, and I think Julian kind of said this, and it's a sort of negative comment, but one thing that worries me throughout all of this is that I work on AGN as objects themselves, and I would say that we don't really have a good model of AGN today. Single black hole AGN. We don't get the spectra very well. We don't really truly understand the X-ray emission. Even the UV is not well modeled by accretion disk models. There's the size discrepancies. There's the changing look AGN and the variability. And so I think one worry we have is that we still don't entirely understand AGN that well. So distinguishing what AGN can do from what binaries do is I think still a big problem that we have to deal with. And we need to understand AGN better.
Yeah, I think we have someone remote, Manuela.
I think Shane covered exactly what I was going to say. Yes, I think we don't understand AGNs. And I would like to ask if there is any plan to include a review talks on AGNs observations in this program, because I think it's relevant to what we're trying to do. I think Shane summarized it fairly well. There's a lot of issues that we still don't understand, but part of them is also due to the fact that the community is. I mean, my understanding, at least from participating to some of these meetings, is that community is not, let's say, too well connected. Also from the observational point of view, so there's a lot of information that needs to be processed also observationally. Is there any plan to have anyone to talk about this?
Is there?
Certainly not this afternoon. But we have many weeks. We can, yeah.
This would be a great thing to get Yante to talk about his AGN simulations.
Yes, let's volunteer him while he's not here.
Yeah,
Great. He will do it, I'm sure.
That's settled.
Yeah, I think that's a very.
I mean, this question of the variability is intriguing, but it could be just very different than just binaries.
Supplement Shane's remark about the contrast, trying to learn something about the contrast between binaries and singles when we barely know the singles. A recent referee asked us the astute question to make a more direct comparison of exactly that sort. And the best we could do was to compare our predictions for a binary with the predictions made for a single based on similar modeling physics, because there isn't any other apples comparison we could make. And it tells you sort of what a primitive state this program is in.
Yeah, I think in the interest of slowly wrapping up and then transitioning to overall discussion and closeout of the meeting, I think there's a lot that we know we're doing poorly or things that we clearly know we shouldn't do, but I guess it's a question of mapping out how we want to move forward from that. Yeah, I think making that a topic for some of the further workshop weeks might be interesting. I think I'll start a document and share it on Slack where we can maybe kind of synthesize some of the discussion we had during this week carrying forward. But are there any kind of last remarks that anyone wants to make? Any questions before we hand over? So,
yeah, I would just say, and a lot of the focus on the relativistic black hole business has been on the binary AGNs, but I think, I was quite impressed by the stellar work, because one can actually see things. You can see things change in time on a graduate student lifetime and so on, rather than on civilization timescales. So it seems to me it might be interesting to start paying a bit more attention. I mean, we don't know of binaries, but things like Cygnus X1 and all the other retreating black hole singles, but making a determined effort to look for both understand the singles better, just like trying to understand the AGN better, but the timescales are much easier to deal with. State transitions are easier to follow, and then perhaps we'll find a binary and we can have tremendous fun with something that changes on seconds to hours rather than years to millennia.
Yeah, definitely second that.
I detect energy going down, so maybe we should wrap up this discussion and get to the last discussion of the meeting.
Yeah, so thank you all. I have good news and bad news. The good news is we don't secretly have planned another 45-minute discussion for you to sit to. The bad news is it means the conference is essentially done. I think, Dan, did you want to say a few words, or did you have a couple things you wanted to say?
Yeah, sure. Well, I think maybe we should be excited about all the things to learn rather than ending on the note that there's a lot of things that we don't know how to do yet. I'm excited about it, and after being here, privileged to be here for the last 4 days with a room of experts on observations, theory, numerics in both stellar and black hole realm, I'm pretty invigorated to think about quite a number of new ways forward. So I hope we keep the discussion on those intersections going. And so I just wanted to thank all of you experts in those areas for being here and making this a really interesting conference. So thanks a lot.
Yeah, and I think just a final note, I know that, some of you are going to be using jet bridges very soon to leave us, and you won't be here in person for the remainder of the workshop. But I would just encourage everyone to please, if you're interested in staying engaged in some fashion, One of the benefits of the pandemic is that we really do have a lot better online access to things. So the vast majority of activities here are going to be available online. So if you want to attend talks going forward, keep an eye on the schedule. You should be able to do that. We also have robust discussion on Slack, especially for those of you interested in doing some of the code comparison work. So again, I really encourage all of you to please stay tuned because it would be a shame to lose your expertise for the remainder of this meeting. Otherwise, I think that's it. Zoltan, do you have any last announcements?
Nothing really. I'm feeling kind of tired because we had so many great talks that I enjoyed very much, and my brain got over-exercised. But it was really great. Yeah. So maybe in terms of the activities, I think I just want to second what Caitlin said. There are two particular things on Slack which I hope people contribute to. One is the code comparison. The other hasn't gotten started as much, but it's the collection of candidates, which Daryl and I started. So I hope at the end of this workshop, we'll come up with some kind of draft where it's more or less complete set of massive black hole binary candidates. But there's going to be other nice discussions as well. So stay in touch.
And I will put on my KITP staff hat and just remind people, if you do work that has benefited from this conference or workshop, please don't forget to acknowledge KITP because they like to have their name listed on paper. So otherwise, yeah, I think there's no formal post-conference beverage or food service, but if you are interested and you're not jumping onto a plane immediately, feel free to hang around and we can certainly try to set something up.
Looking forward to it.
All right. Thanks, everyone.
Thanks.